this is the last talk of the session, so I'm going to try to be as clear and as straightforward as possible. This talk is actually has some connotations with the talks already said here, with the talk of Ronaldo Vieira, also disks around a central gravitational source, and also disks around the central gravitational source with relativistic consideration. Or this was not a disk but a ring, and I used the same ring. So a lot of the talk has been already said. So I will have some more time for the details actually. So that's nice. The structure of the talk is straightforward. I will introduce the context, the studied fields, then some technical notes, and present my results and Poincare surfaces of section. So the context is already mentioned. Gravitational effects of mass, of non-central mass in numerous astrophysical situations is neglected, and the group around Oldřich Semerak at the Prague Institute of Theoretical Physics concentrates on the effects of the mass around the equatorial plane, on the geometry and on the motion, and me specifically on the motion. So some context, Semerak and Suková already studied a fully relativistic model of this geodesics, free particle motion, and the symmetry was axial and it was static, which is not so realistic, but you have seen that the metric, the Weil metric, is very simple then, and it was a demonstrative model for demonstration of the fact what happens when you place matter on the equatorial plane, and they used the Weil coordinates as already stated and superposed the just investigated Bach-Weil ring and a family of disks which are quite realistic, however they have a surface density, also as with Ronaldo. And here is the metric. We already saw this. This is actually the Laplace equation in vacuum. When there's mass, it works as with mass. It looks exactly the same as Laplace equation in Newtonian gravity. So it's great that we can use the new functions as Newtonian potentials of the same situation. However, there is a problem with interpreting the Weil coordinates as Newtonian, because you can see that they do not transform as spherical from the Schwarzschild coordinates as if they were cylindrical. So if we want to interpret the situation in a Newtonian analog, there will always be an arbitrary element. There will be a conventional element. It is the same letters that are used here, but the Newtonian situation cannot be straightforwardly drawn from this. And this is manifested, for example, by the fact that the black hole horizon looks only like a bar in the Weil coordinates. So this is very different, and we cannot quite Newtonize the space-time. So we do it very naively. We do Newtonian dynamics with Paczynski beta potential, emulating the Schwarzschild black hole, and then use the Newtonian potentials of the formally same masses of the disk or of the ring to simulate the test particle simulations. There are some integrals of motion, this is the notation, and the trajectories are independent of the particle mass, so we can forget the mass of the particle because it's a pseudo-gravitational theory, so it's just test particles in a gravitational field. And why do we do this? It was to compare the model with the relativistic one, obviously, and to demonstrate the robustness of the fact of chaos happening in these spacetimes, or in these models of a black hole with a disk or ring. So I'm not going to show these new potentials because they are rather non-simple, but I will show some graphs. So here the disk, the superposed disk, starts at rho equal to 20, and here is a moderate potential well, and it falls off, so it's quite realistic, the potential. However, as stated already in the previous talk, there is a cusp on the equatorial plane, which corresponds to the fact that when you pass through the disk, the force switches direction. The force is always pointing into the disk, so it switches direction, and this makes the model less realistic. However, we tried it because that's the best we have. The Bach-Weil ring, the potential is singular, so perhaps this could be used as an outer solution of gravitation for a torus type of accretion disk, but not for a disk which is more spatially smeared. So notes on realization. We integrated the equations of motions numerically. However, you have seen that the potentials aren't really nice. They are extensive formulas, elliptic integrals, and so on. So there were some difficulties, which you can see there are some artifacts in the images, which I will show. And we have used Poincare surfaces of section to visualize the motion, which, if there are people who don't know this, they are constructed by putting a plane in the equatorial plane, and whenever the trajectory crosses the equatorial plane, these two coordinates are noted, and you have to believe me that it is constructed so that it is a one-to-one map. Every point on the map corresponds to another point after one iteration. So it's really a map, and it can be considered like a map problem, and it is a full characteristic of the phase space. It is constructed so that it can really give an image of the phase space, a complete image. So we did only a qualitative comparison so far. This is work in progress, and however, a quite thorough qualitative comparison, as you will see. And we have studied the dependence of the surfaces of section on the mass of the disk or ring, on its radius b, and on the angular momentum and specific energy, specific angular momentum. And all of this is stated in units of black hole mass m. That is half of the gravitational radius. So this is quite natural, and we use geometrized units. So you have to kind of calculate back to some real physics, but it is it is a simplification. So let us see the sequence of the surfaces of section. It is the disk superposed with the black hole spacetime. Here is the formerly stable circular orbit, and these are just small quasi-periodic oscillations around it. And in the beginning, when the perturbing disk is very light, it almost doesn't modify the phase space. But you will see in the sequence, note that the axis change. It wasn't done for animation, but note that it changes the phase space a lot, the mass on the equatorial plane. So this is just to get a flavor, and you can see in the top that the mass varies quite crucially, and this is one and a half of the black hole mass. So this is not really astrophysically correct, but it is also done because of a theoretical stance on the problem. So just some comments. These are chaotic areas of the surfaces of section, and the particles, when they become chaotic, they fall into the black hole. So what we see here is that the particles fall into the black hole much more because they become irregular. However, the regular orbit infinitely. So this is important for astrophysics, that actually there is non-viscous accretion actually of test particles, which would not accrete or say fall into the black hole when the perturbation wouldn't be there. But however, this is not a realistic model, it's a demonstrative model. So we will discuss now the correspondence of the surfaces of section. Here on the left we have always the pseudo-Newtonian or the Newtonian model, and on the right we have the relativistic model of Semerak and Suková. And you see that there is always an analogy, but you see that the particles are closed off from falling into the black hole from the beginning. So this is a feature of the Paczynski beta potential. It doesn't reproduce the structure of the phase space so well. So you can see when this curve is closed, the particle cannot get into there. It's just oscillating, quasi-periodically orbiting. However, in the Paczynski beta, even for zero perturbation, the phase space is open. So here actually are non-quasi-periodic trajectories which would start from the black hole, kinda orbit for a while and then fall into the black hole. And the chaos is causing the effect that the particles from the edge become chaotic and fall into the black hole. They orbit into the black hole and much more slowly than the normal in falling black particles. And you can see that even for growing perturbations, this is 0.3, this is 0.6, there is a clear analogy. There is this free periodic island, which is a special quasi-periodic stable orbit, which generates some oscillations around it, and in the relativistic case also, which is unexpected analogy, because these are completely different equations, completely different models, and you can see that this analogy holds even for stronger perturbations. We have here quite strong perturbing masses, but and they are not the same. I shifted them slightly to fit better, but you can see that the analogy is clear. The nonlinear resonance corresponds. So the Paczynski beta actually resonates with the disk potential in the same way as the Schwarzschild black hole, which is very unexpected. And you can see here again that the same number, the same resonance rises around the disk being as massive as the black hole. So this is very surprising, and it continues until very strong perturbations, and then the situation changes. But this is to be expected. This is better than we wanted, because when the disk has the mass of the black hole, obviously relativistic effects should take place. But until very strong perturbations, the qualitative structure of the phase space is very similar. So how much time do I have?
5 minutes.
5 minutes. Okay. So I'm just going to discuss some conclusions. So I have just shown the disk superposition. The ring has a much stronger effect on the phase space. It's a stronger perturbation, a stronger source. And however, also there were analogies. Also, the correspondence was more than expected, but it is a strong source, and it doesn't work so well actually. But even for the disk, it is a miracle that this exists. So here are some conclusions. There is an inherent discrepancy between the Paczynski beta potential with the Schwarzschild spacetime. We plan to test some more pseudo-Newtonian potentials, to test the potentials or to find the potential which is best for this kind of correspondence. However, what we want is the angular momentum dependence. That is when we have a certain angular momentum for the phase space to be closed off, for the centrifugal barrier to have a similar effect on both the potentials, on both the effective potentials. And there is also the fundamental issues of scaling of the physical quantities, which I already mentioned. And this has influence on the B dependence and the energy dependence, obviously, because energy is something completely different in both cases. But the B dependence is a great problem, because as Marek has noted, for example, for the Bach-Wild ring, we wanted to measure the physical distance from the horizon to the ring just by integration of the length. The length would become infinite in the relativistic case. So we don't know how to define the radius of the ring. Actually, we have no idea. So we use this formal correspondence. The same letter in the coordinates means the same letter in the Newtonian case, but I mean, this is a weak correspondence. It's conventional, and this is done often in astrophysics. The same letter means the same in both cases, but you can see that this is problematic, and there are some unresolved practical issues. You have seen that this was just counting circles so far and waving hands, but some quantitative conclusions and some real physics should be drawn from this and astrophysical applications. However, as stated, the analogy is strong, and chaos was found in both cases, and it is a fact of these kind of models. However, in relevant astrophysical applications, mostly weak chaos is suggested by these models, because you can see that, well, for these perturbations, which are really strong, the chaos is very weak. So this is everything that I wanted to say, and thank you for your attention, and I want to thank the organizers for this great opportunity to talk here, and I think that I speak for all the students when I say that we greatly appreciate this opportunity. So thank you.